All right, so if at any point you have any questions, feel free to stop me and ask me questions about it. Just a quick refresher, and maybe some of you guys were here last time, some of you guys didn't. Just as a reminder, we went over bromination and chlorination. So, and as well as radicals, carbocations, trends like that. But just a reminder, bromination is endothermic, and chlorination is exothermic. You might have seen this in your PowerPoint lectures. I have seen it show up on previous like multiple choice conceptual questions with certain professors, maybe in a quiz, maybe during an exam or an old practice exam. But just in case you need to know, that's the relationship. And then you might also get confused what Me stands for. That means methyl. And Et equals ethyl. So don't get tripped up with that. It's not a new compound or anything. And then just to quickly go over all the possible rankings in this unit, there is radicals, basically what we went over last time. This includes like chlorination, bromination. There is the carbocation versus carboanion ranking. There is E ranking. There is nucleophilicity ranking. And what that ranking is, it's basically identifying, they give you a set of nucleophiles and they ask you to rank what is the best nucleophile versus what is the weakest nucleophile. There is also heat of hydrogenation. Some of these you haven't heard yet. Don't worry, you'll get to it. Heat of hydrogenation is when you get to alkenes, which is chapter 8, I believe. Hydrogenation. And in heat of hydrogenation, you'll also talk about alkane stability and / reactivity. There's an inverse relationship there. And then, of course, SN1, or I'll just write in mechanisms. So they might just simply ask you rank by SN1 or rank by SN2. So there's like a full complete list for this whole unit. And of course, as always, you're always going to have acidity and basicity ranking, so just be prepared for that. And then I want to quickly go over the periodic trend, bean. Some of you guys might have heard of it, some of you guys haven't yet. In this unit, we'll talk about the one trend or corner that we haven't discussed in Unit 1, which is the N, which stands for nucleophilicity, okay? So a question about the trend, obviously it goes this way. As you go down and as you go to the left, it increases in nucleophilicity strength. But some other things are negative charge is better than no charge. And in addition to that, resonance is actually bad. Sorry, I think I cut off. But what I was trying to say is resonance and inductive effect is actually bad for nucleophilicity. Okay. Anyone know why it's bad? Okay, basically, resonance is bad because nucleophilicity, you want it to have a strong negative charge. And what resonance and inductive effect does is it reduces that negative charge, and it weakens its strength. So you don't want that. Nucleophile, you want the negative charge. You don't want to keep it stable. You want it to be reactive so it can go in and attack a carbocation. Okay? Hopefully that made sense. If not, let me know. And then lastly, the less bulky you are, or less bulky is better than more bulky. Okay? And the reason for that being is if you have less electron cloud, you can easily attack and reach in those places that contain a carbocation. If you're more bulky, it's harder for you to reach those places. Okay, and in terms of atoms, here are the top 6 that you'll mainly deal with: Si, carbon, phosphorus, nitrogen, sulfur, and then oxygen. Okay. Obviously, this side being the most nucleophilic, and this side being the least nucleophilic. Okay. Yeah, I have a little bit of cold. All right. So, any questions on nucleophilicity before we get into comparing SN1 and SN2? We're gonna create some sort of flowchart. Okay. All right. So I'm gonna write SN1 on the left side in red. I am gonna write the word tools in black in the middle. And I'm gonna write SN2 in blue. Okay, so let's go down the list of tools and see what we are comparing between SN1 and SN2. Okay, and the reason why we're doing this is because the entire exam is based on, can you identify which mechanism to use in a reaction? Okay, there are certain indicators that will tell you whether it's SN1 versus SN2, and these are what we're going to discuss right now. Okay, so first off, sorry, 1 second. So first off, we're going to discuss the position. And when I mean position of leaving group. Okay, and then I'll adjust it all later. Okay, the nucleophile strength, is it weak? Is it strong? Solvents we are using: polar protic, polar aprotic, stereochemistry, rearrangement, the leaving group preference, how many steps it has, the rate law, which is entirely not too important, but you might occasionally hear about it in lecture. And then, of course, the graph. Again, not entirely too important, but you might see it in lecture. All right, so here are about nine different tools that you can use to see if it's SN1, SN2. So let's go down the list. For SN1, the position of the leaving group is going to be preferred to be 3, 2, 1. Okay. nucleophile strength is going to be weak. Solvent is going to be polar protic. When I mean stereochemistry, does anyone know what I'm asking for? There are two options. Sorry, I think my mic cut off again. So there are two options. You can be inverted or inversion, or you can have a racemic mixture. Which one is SN1? Anyone know? Mm-hmm. Right, I think you meant to say racemic mixture, which is what that is. Basically, what racemic mixture is. Racemic. It means you get both the wedge and dash formation. Okay. In terms of rearrangement, yes, there is rearrangement, and there is a methyl and hydrogen shifts. Leaving group preference, it goes iodine, bromine, chlorine, and then fluorine. Okay. SN2 actually, sorry, SN1 has 2 steps, and we'll discuss each of those steps after. Now, the rate law, you might not know this, but it is K and then the electrophile. Now, the graph. So the graph, I'm going to draw. Now, once again, you might not need to know this, but it wouldn't hurt. So you have one transition state, you have a second transition state because you have 2 steps. Okay? And then this in the middle is going to be your intermediate, which is when your carbocation forms. Okay? And once again, this is your first transition state, this is your second. Your reactants are here, your products are here. Okay? So once again, SN1 has an intermediate, and that intermediate is the leaving group leaving and the carbocation forming. The formation of the carbocation is your intermediate, and M has 2 transition states because it has 2 steps. The rate law is dependent on the electrophile. All right. So, any questions on SN1 before we get into SN2? Okay, that should be fairly standard because that should have been the first thing you guys have learned. So I'll get into SN2 now. So SN2 is going to be almost completely opposite. Instead of 3, 2, 1, it's now going to be 1, 2, 3. Nucleophile, instead of being weak, it's going to be strong. Solvent, instead of being polar protic, it's going to be polar aprotic. And we'll discuss what protic and aprotic means later. Stereochemistry, instead of racemic mixture, we just talked about it, it's called inversion. and we'll also talk about that. Basically, if my leaving group is on a wedge, my product should be on a dash. When the nucleophile attacks, nucleophile should be on a dash, and then vice versa. If my leaving group is on a dash, when my nucleophile attacks, it should be on a wedge, if it is SN2. If it's SN1, you just keep the same stereochemistry. And then, is there rearrangement for SN2? The answer is no. Only SN1 and E1 can do methyl and hydrogen shifts. Leaving group preference is going to be iodine, bromine. It's going to be the exact same as SN1. Steps, it's going to happen in one step actually, and then the rate law is going to be K again, electrophile, and nucleophile. Okay, so you might get some questions regarding the rate of the reaction, and they'll ask you to compare different things. They'll ask you, okay, if I change the solvent, how does that affect if I change the nucleophile from weak to strong, if I change the position of the leaving group, stuff like that. And then if you change anything with the nucleophile, that means SN2 is going to get affected. Changing the nucleophile for SN1 doesn't really affect whether it increases or decreases the reaction rate, only if you mess with the electrophile, which is changing the position of your group. All right, now on to the graph. It's very similar, except instead of instead of two transition state, it only has one, and of course, no intermediates between, because it only has one transition state. Okay. All right. So I highly recommend knowing all of these. It really makes a difference in knowing or getting the answer correct, first of all. But if you mislabel any of these, first you have to identify correctly what tertiary means, what a weak nucleophile looks like, what protic versus aprotic means, how to rearrange, stuff like that. So that's the first step. So knowing all that knowledge, then you have to be able to distinguish or look at a problem or a reaction. You have to look at the electrophile, you have to look at the nucleophile, and then identify each of these tools and puzzle pieces, and then put it together and be like, okay, it's a strong nucleophile and it's a polar protic, so it must be SN2. So in my product, I'm going to invert, the nucleophile is going to attack, replace the leaving group, and I'm going to invert the stereochemistry. Okay, so that's kind of the thought process that you guys should be having, and like the, I guess, timeline of studying should go, at least between SN1 and SN2. E1, E2 is not very different. We'll probably get into that next week, but I'm going to draw a very similar comparison, like chart. But yeah. Any questions on any of these? I'll get into how to distinguish weak versus strong nucleophile, and how to distinguish between protic and aprotic. I think those are probably the main questions you guys have. Okay. All right, one moment. All right, so I'm trying to make sure everything's on the same page, so I'm not trying to clear the whole page. So I will try to put this off to the side. Um, so let's look at strong versus weak nucleophile, and it's very simple. Or actually, let's first look at polar protic versus polar aprotic. Polar protic has these specific um, solvents. It's usually your methanol, ethanol, some type of alcohol. And of course, it also has water. It has water and carboxylic acid. So if you see a pattern here, they all have the OH. They all have the hydrogen bonding, okay? So if you have a hydrogen bond and it's reacting with itself, it should form a hydrogen bond with itself, okay? That's what protic means. And then of course, aprotic means it can't do that. It cannot form a hydrogen bond with itself, okay? Some examples of aprotic solvents are DMSO, DMF, and then acetone. Okay, these are the most common ones. There might be more, I'm not entirely sure. At least I can't remember any at this moment. But I believe your lecture PowerPoint should have most of it. Okay, so if you see any of these underneath the arrow, that should be your solvents. And if you see any of these, it's going to be protic. If you see any of these, it's going to be aprotic. Okay, and then let's quickly go over the arrow setup. So okay, you have a box right here, that's your starting. You have an arrow, and then you have your final product, right? Okay. So this is called your this is called, yeah, so this is called your uh, starting compound. This is your ending compound or products, and this is called your reagent, okay? Now, typically, your electrophile is contained here. However, your electrophile can also be contained here, okay? The electrophile contains your leaving group, okay? And your leaving group is always going to be a well, not always, but like most of the time, it's going to be some type of halogen, okay? Sometimes it could be water as your leaving group, but that requires extra steps. And then, of course, above the arrow is going to be your nucleophile. So let me write that down. And these are typically, okay, but you can see the nucleophile here as well. These could be interchangeable, but most of the time you see your nucleophile there and your solvent here, okay? And then let me type in electrophile here. Okay, and then of course your product here. And then like I said, these can be interchangeable. Okay. And then leaving group is in your electrophile. right? So your leaving group is not the entire electrophile, okay? So for example, if I do this, and then I have, let's say, CH3OH. So let's say I have methanol. Now methanol can be a nucleophile or it can be a solvent. In this case, it's acting as a nucleophile. Your solvent is not always apparent, or it's not always there or given, but most of the time your nucleophile will always be there. Okay, so, but yeah, again, in this case, this whole thing is your electrophile, but only the bromine is your leaving group. Okay. All right. Hopefully that makes sense. And then, of course, your final product is OCH3. Okay. So once again, to get your nucleophile, you have to separate your H and the rest of your compound to get a negative charge on oxygen. Okay. Now H separating is not is a weak separation compared to Na, sodium. Sodium separation is a strong separation, or dissociation rather. Okay, so the H and bromine leave and they create a side product or a byproduct, which you don't ever need to concern yourself about, but it should always create some type of compound that makes sense. Make sure put methyl instead of, make sure it's OCH3 and not just methyl. Okay. Now, to identify weak versus strong, it's literally all in H versus Na. It's just if H dissociates, it's going to be weak. If Na or K dissociate, it's going to be strong. Okay, and the reason why is because these are strong electrolytes. Okay, or compounds with Na and K form ionic bonds, and when the ionic bonds dissociate, they have a complete separation of charge. Okay, so all of the negative electrons go to the nucleophile. Okay, while Na and K have all of the positive charges. Whereas in H, only partial dissociation occurs, so only partial negative charges go to the nucleophile. Okay, that's why it's considered weak. Okay? Does that make sense? All right, perfect. All right, any other questions about any of these? I think the rest should be pretty self-explanatory. What is the N? What is that N that starts with Si? Oh, okay. This is nitrogen, or this is like the trend for nucleophilicity. So if you have like a P, right? Yeah. Okay. All right. I believe that's all I'm gonna do for today. This I'm just gonna go over SN1, SN2, which I already did. I explain nucleophile versus solvent. Hopefully you guys understand what rearrangement and how stereochemistry inversion looks like, and the rest of these four should be pretty self-explanatory. Okay, but if you guys have any questions, let me know. I'll stick around. If not, I'll see you guys next week for E1 and E2. And of course, the recording is going to be posted on YouTube. Yeah, no problem. Thanks for coming. I'll see you guys next week.